Okay, so we should be live now, everybody. I will ask my student colleague if he can confirm that he can hear good audio. Clelia, maybe you can say just a couple of test words to make sure that the audio is okay.
Okay, can you hear me?
We have to wait. There is a delay of about 30 seconds to the stream.
Okay.
Okay, but can you hear Clelia?
Can you hear me?
Okay, so the audio this time seems to be working all right.
Okay.
With that, I think we can just start the session. I welcome you all to the second session of WeSST 2022. My name is Michael Woloch. I'm an independent postdoc in the Quantum Materials Modeling Group of the University of Vienna. And together with Martina and Norbert, I'm the organizer of WeSST this year. And I will be chairing this seminar today. You might not see me as large as you would hope. In your window, you're seeing Martina right now, I think. That's because I'm also streaming the sessions on YouTube and organizing that. But I think you can live with that, not seeing me full screen. I hope so. So maybe Martina and Norbert, my co-organizers, can quickly introduce themselves for those who did not see the first session. So just a couple of words, please, from you two.
Hello, everyone. For whom wasn't attending last session, my name is Martina Stella. I am a Boltzmann Research Fellow at ICTP, and I work mainly on developing the FT methods for excited states and sometimes to tribology. And I welcome you all to this second session of WeSST. I hope you enjoy the great talks we have upcoming.
Yes, hello from my side as well. My name is Norbert Bader. I am currently postdoc at the IMKT Leibniz University of Hanover, studying EHL contexts mainly. And I also welcome you and hope that today's session will be as exciting as our first session.
So, then I want to say that this year's topic of the seminar series is Tribology Applications of Big Data, High-throughput Machine Learning and Artificial Intelligence, which you probably already know. And we have in total 3 days of seminar. This is the second day, and the last one will be upcoming Friday, October the 14th. And the format, if you don't remember, is we have 2 invited speakers for each session, and then 3 flash talks in the middle. And without much further ado, I want to introduce the first invited speaker today, which is Professor Maria Clelia Righi from the University of Bologna. As I said, she's a full professor at the Department of Physics and Astronomy at the Bologna University since 2020, after winning an ERC Consolidator grant for advancing solid interfaces and lubricants by first principle materials design, or SLIDE, which is a very nice acronym. Before that, she was a professor at the University of Modena in Reggio Emilia since 2016, and I had the great pleasure of working with her there as a postdoc from 2017 to 2019. She is also a visiting professor at the Imperial College London and collaborates with different multinational companies, for example Total and Toyota. And she's on the number of editorial boards and has given a numerous invited talks, for example at the Gordon Conference, the MRS Spring Meeting, and maybe most important of all, at WeSST before this one. So Clelia is renowned for her pioneering work in ab initio tribology and also tribochemistry. And I know for a fact, because I worked with her on it, that she has been interested in high throughput methods for some time. So her work is an excellent fit for this year's topic. And yeah, her presentation will be entitled High Throughput Screening of Adhesive Friction in Solid-Solid Interfaces. And with that, I invite you to share the screen, Clelia, and start your presentation.
Okay, let me share the screen. Okay. Can you see my screen?
Yes, I think we can.
Okay. So thank you very much. Nice introduction. And so I am going to present the results of a work on high throughput calculation, as you mentioned, that was started also in your collaboration. So I'm very happy to present in this conference that you organized. You know very well that integrating experimental tools with computational experiments with computational tools and digital data is nowadays considered a key strategy to reduce the time and costs for materials discovery and deployment. In this context, high-throughput calculations based on solving the fundamental equation of the Schrödinger equation for the many-body system for many materials in parallel in a relatively short time is considered acquiring very importance in this context, and they have been successfully applied to improve and also discover new materials for several applications. I would like to use the pointer. Let me see if I can. Can you see my cursor, or should
Clelia, I see your presentation not in full screen.
Ah, really?
It's just my problem. I'm not sure.
Ah, thank you, Martina. Let me disconnect from the. We tried previously.
Yeah, now it's
Okay.
now it
Yes.
works. Now it's fine.
Okay. Thank you for giving me the possibility to change. Okay, so this is the idea of high-throughput calculation, and they have been applied successfully for designing materials for many applications, from hydrogen storage to catalysis. And what we want to do is to apply high-throughput screening of solid interfaces. This in particular for tribological applications. So this is one of the aims of the ERC project slide that you mentioned. So we have started this project even before my ERC started. We developed an initial workflow. First of all, I introduced a protocol to derive two important tribological. Can you see me?
Yes.
Okay. So first of all, I introduced a protocol to calculate two very important figures of merit in tribology by first principle calculations. The work of adhesion, that is defined by as the energy required to separate two surfaces from contact, and the ideal shear strength, that is the maximum resistance to sliding of an ideal interface. This can be calculated, first of all, by calculating the adhesion energy as a function of the relative lateral position of the two surfaces, thus constructing what is called the potential energy surface or gamma surface of the interface, that describes how the adhesion changes as a function of the relative position. And these energy variations give rise to frictional forces. Indeed, by selecting a potential profile along a specific direction and deriving it, it's possible to monitor the forces that are present during the sliding motion. And we consider the most negative force divided by the area as the ideal shear strength. So the maximum shear strength that the interface can resist before start sliding. So the most relevant path among the different possible paths is the minimum energy path that connects the path minima passing through the saddle points. And this path can be automatically identified by different methods. We consider the zero temperature string method, and implemented it in our first version of the workflow that was composed by 4 different units. There was, first of all, a set of very limited number of input parameters is read. Then there is a bulk unit where the bulk properties of the elemental system considered are calculated, and the computational parameters are optimized automatically. So the optimal kinetic energy cutoff, the optimal K-point density are identified by using the Concham equation of states to describe the bulk. That allows also to calculate the theoretical lattice parameter and bulk modulus. Then the surface properties are calculated. In particular, the surface energy is obtained, and the thickness of the slab that is used to model the surface is automatically optimized by converging the calculated surface energy. And then the interface is automatically constructed, and tribological properties as the adhesion and the shear strength, but also electronic properties such as the electronic charge displacement that I will describe later, are automatically computed. So we apply this workflow, first of all, to study the properties of homogeneous interfaces that are interface like iron on iron obtained by mating two equivalent bulk materials. For each material, we consider different possible surface orientation. In these tables, I am reporting just the most stable values, so the value of the adhesion for the surface that turned out to be more stable. So on the left, I report the adhesion energy, and on the right, the corresponding ideal shear strength. So you can see that the color code, where the darker color indicate higher adhesion, immediately reveals that transition metals where the d orbitals are not fully occupied have the highest adhesion, and this is also reflected in the shear strength. So immediately we realize that there should be a correlation between the quantities. And so we calculated the cleavage strength, that is the maximum resistance to cleavage of the two surfaces, a function of the adhesion, and the shear strength is a function of adhesion. And we found that there is a linear correlation between the first two quantities, as one could have imagined, while the relation between the adhesion and the shear strength is a power law that we identify in this way. So this analysis allows us to calculate the shear strength of an interface by knowing just its adhesion, which is much more easily calculated than the wall potential energy surface and the shear strength. But the analysis of the data are also relevant to understand the mechanical properties of materials. For example, here I have reported the ratio between the ideal shear strength and the cleavage strength. And you can easily understand that when this ratio is high, that means that the failure mode of the material will be a brittle cleavage, because it's very difficult to shear while it's more easy to cleavage. While the opposite situation of low values of this ratio indicates a ductile failure, because it's easier to create a stacking fault to nucleate a dislocation instead of a crack. So you can understand that by analyzing the database obtained by means of high-throughput calculations, these general relations can be identified. These are just some few examples, but relevant because these parameters can also be used in macro-scale models, where very often the materials properties related to the microscopic details are not taken into account, and parameters such as the adhesion, the ideal shear strength are empirical or just qualitative description. We then studied the relation between the interfacial property, tribological properties, and electronic properties to understand the fundamental origin of the adhesion and the shear strength. In particular, we analyzed the electronic charge distribution. On the left, you see the planar average of the electronic charge distribution along the direction perpendicular to the interface. I'm considering an iron bulk that is obtained by mating two iron surfaces, here represented. Can you see my cursor?
Yes.
Yes.
Okay. So you can see that when mating two surfaces, a redistribution of the electronic charge occurs because this spilling off of the charge is removed and a charge is accumulated at the middle of the interface. So this electronic charge redistribution can be calculated precisely in the same way as the adhesion energy is calculated. That is, by subtracting from the total electronic charge of the interface the electronic charge of the two separated surfaces. And so here there is a representation of this charge redistribution, and we define its integral in the interfacial region of the absolute value of this difference as the total amount of charge that is redistributed when an interface is formed. And we found that this amount of charge that is redistributed, that is mainly accumulated at the middle of the interface, has a linear correlation with adhesion. And this holds true for different interactions. We found this for layer materials, for metallic materials, and for covalent materials. And so the adhesion is dictated by the amount of charge that is accumulated at the interface when the interface is formed, basically. And this understanding is very useful to design specific surface chemical modifications to prevent this charge flow from the bulk to the interface. For example, if we cover an iron surface with sulfur atoms, and we mate it with a clean iron surface, we can see that the charge distribution is much lower. This scale from 0 to 10 is lower than this one, that the charge distribution that occurs for clean iron. And the adhesion is reduced is highly reduced, and this reduction reaches one order of magnitude when we cover the two iron surfaces by graphene, and also the charge accumulation at the middle of the interface is highly reduced. The same holds, for example, for diamond on diamond has a very high adhesion, while hydrogenated diamond has a very the adhesion decreases almost by 2 orders of magnitudes, and this is because the charge that can accumulate in the interface is much lower than in clean diamond. So this fundamental understanding is important to design, for example, lubricant materials that are necessary to reduce friction in sliding contact. Indeed, we discovered that this electronic charge distribution is connected not only with the adhesion, but also with the frictional forces, because we analyzed the amount of charge that is present in the interface when the two surfaces are stacked in such a way that we have a minimum in the potential energy surface. This amount of charge is higher than the amount of charge that is at the interface when the surfaces are on a maxima of the potential energy surface. So when a slider moves on a substrate, there is a charge redistribution during sliding, and this charge redistribution dictates the appearance and the magnitude of the frictional forces, because this is the origin of this minima and this maxima, and as I explained before, this feature of the potential energy surface are directly related to the shear strength. Okay, then after considering the homogeneous interfaces, we consider heterogeneous interfaces that are obtained by mating two different crystals. And for example, here I'm representing copper on iron. And as you can understand, the situation becomes much more difficult because we have to mate two different crystal lattices, and the calculation can become very computational demanding if we want to minimize the mismatch between the two mated surfaces. In order to define a common supercell for the two lattices, we adopted the Zur algorithm that was developed in the past and was implemented in a library that we included in our workflow with some modification. That is the MPI interface library. And this algorithm allows to identify the supercell, the common supercell to the two different lattices once a threshold value for the mismatch is identified, is provided. So in our workflow, we select a threshold value for the acceptable mismatch, and then the Zur algorithm automatically identify the minimum supercell area in plane area that can accommodate the two lattices with that given mismatch threshold. For example, here in black, you can see the supercell that has been identified for this couple of lattices. So the lattices are automatically rotated, for example, one with respect to the other, to obtain the minimum size for the common supercell. And once this supercell is identified, our workflow is able to calculate the PES, the potential energy surface, for the hetero interface. This is done by identifying the high symmetry points of each lattice. For example, here I'm representing copper on aluminum. So we have this common supercell. This is this rectangular cell where the high symmetry points of each lattice are indicated, and when the two surfaces are mated, the energy is calculated for every couple of symmetry points. So by shifting the on top side on the hollow side of the second surface, on the top side of the second surface, so all the possible pairs are considered, and replicated within the common supercell. And this allows us to obtain the potential energy surface for the heterogeneous interface. So all this has been implemented in a very advanced computational code based on Python, which is composed by three main units. We have a computational kernel where the input-output handling when considering the most used software packages for materials science, such as WeSST, Quantum Espresso, LAMPS, are automatically constructed. Here, the PyTmagen and MPI interfaces are used. Indeed, the interface, the surface, the interface are automatically calculated, as well as the tribological and the electronic properties that I described before. There is a high-throughput unit that is based on the Fireworks library that allows to create, manipulate, and execute complex workflows. And finally, there is a navigator that that manages the interaction with the database. So the reading from open database and storing the data, and this is a very delicate part of this machinery. So we devoted a lot of effort in developing this navigator for managing the data and also the provenance of the data. Okay, so we applied this software to calculate the adhesion of heterogeneous interfaces. We started by considering metals because they are technologically relevant. Indeed, the results that we obtain can be used also to understand not only tribological properties of materials, but they can also provide some insights in metallurgy, because they provide information such as the solid solubility of a material when an alloy is formed from two different metals. So you can see that we reported on this diagonal of this table the energies of the homogeneous interfaces that correspond to double the surface energy of these materials. And so you can easily observe that, as noticed before, we have higher values for the adhesion when transition metals have partially occupied the orbitals, while when the orbitals become occupied, such as in the noble metals, the adhesion decreases. And the adhesion of heterogeneous interfaces is somehow a mixture of this behavior. Okay, so it's also possible to understand this by simply observing this color code. So, first of all, this is an interesting result, the fact per se that we have provided these numerical values for the adhesion, because up to now, it was not possible to find in textbooks a systematic description of the adhesion of material space. What we found is just a qualitative description proposed by Rabinovich, who described this quantity, the compatibility of two different metals by considering the solid solubility that can be measured in the experiments. So the material pairs that are defined compatible are those that have a solid solubility higher than 1%. Partially compatible, those that have the solid solubility in this range, and so on. So by defining this compatibility, a let's say, guess on the adhesion energy, according to this author, could be proposed by this simple relation between this compatibility and the surface energy of the two metals. So as you can understand, this is just a qualitative description. So having accurate values, because again, we are performing first principle calculations. So we are able to describe accurately the chemical interactions at the interface, is something that can be useful for also engineering models, macro scale models. And but the idea of describing the adhesion in terms of the properties of each material is very interesting. I will come later on this issue. We analyzed if the relation that we found for homogeneous interfaces between the charge displacement and the adhesion energy holds true also for heterogeneous interface. And this is the case, as you can immediately notice by comparing these two graphs, where we reported again the adhesion energies and the calculated charge displacement as described by this formula. And this is also visible in this plot where the correlation index is 0.75. So these results confirm that the adhesion of heterogeneous interface is directly correlated by the amount of charge that is accumulated in the interface when the two surfaces are mated, as it happened for homogeneous interfaces. As I said, it's interesting to find to identify a relation between the adhesion and that is an interfacial property with the property of the single materials that are paired. So, as you probably know, this is the expression that relates the interface energy, gamma 1, 2, with the surface energies. So it's clear that where the interface energy basically is the energy cost or gain to pass from an elemental bulk to an interface. So to remove bulk bonds and create interfacial bonds. In analogy with the definition of surface energy, that is the energy cost, in this case, to create a surface, that is to remove completely the bulk bonds on the surface. So it has been suggested in this book by Israelachvili that the interfacial energy, the interface energy, which is not possible to directly measure, can be related to the surface energies in this way. So by substituting this in the expression for the adhesion, we obtain that the adhesion should be equal to the geometric average of the surface energies. So this is something that we immediately try to check, to verify. And indeed, by plotting the adhesion as a function of the geometric average of our ab initio data, we found a good correlation, 0.8, the correlation, and the root mean square error, that is 0.57. So this suggests that indeed the adhesion could be calculated once the surface energies are known, and these are typically known also for experiments. But we wanted to see if something better could be obtained by applying machine learning. So we adopted the Sur-independent screening and sparsifying operator, the acronym is SISO, that allows to extract effective materials descriptor out of a large number of possible correlated features of materials. And it also allows to identify the relationship between the wanted properties, such as the adhesion energy and the descriptors, in terms of an analytical equation. So both the analytical equation and the descriptors are identified. So it's very smart, this algorithm. So we consider different possible descriptors describing the properties of the two separated surfaces, because as I said, we would like to provide a prescription to calculate the adhesion just from the properties of the two separated materials. So we consider the cohesive energies, the bulk modulus, again, the surface energies, the atom density at the surface, the difference in the electronegativity of the two elements, and both the arithmetic average and the geometric average of all these parameters. So we had a list of almost 20 parameters, and thanks to the SISO algorithm, we could identify, first of all, that just 3 are the relevant parameters: the geometric average of the surface energies, the geometric average of the cohesive energies, and the geometric average of the bulk modulus. The other descriptors are less relevant. Indeed, what we found, including the other description, were very similar to what we found just considering this 3. So, because it is already embedded in, for example, the difference between the surface energy and the cohesive energy, the information on the atomic densities, the geometry, and also in the bulk modulus, the possibility of the two surfaces to adapt each other. So and the algorithm proposed different analytical expressions of increasing complexity that we call phi0, phi1, phi2. But yeah, the correlation index was already very satisfactory for a linear correlation that we prefer, because we can also provide a physical meaning to this expression, because it's clear that the adhesion energy increases as the surface energies. Indeed, the coefficient is negative, because we define the adhesion as the energy gain, and also it's proportional to the cohesive energies, but it's while the bulk modulus is provide a positive contribution, because as harder are the two materials in contact, and as more difficult they can adapt to decrease their interfacial energy. But this the coefficient is very small in comparison to the other two, where the surface energy dominates. So this is an example of what can be done when databases are constructed, and this is what we are also trying to do by considering chemical modifications of our surfaces, because in the past we found that by modifying chemically the two surfaces in contact, the adhesion can be really tuned. For example, we found that by covering the two iron surfaces with 1/4 of monolayer of phosphorus, the adhesion of iron decreases to half of its value. And by including the same quantity amount of sulfur atoms, this decrease is of 1/4 of magnitude. So the idea is that to try to perform an high-throughput screening of possible adsorbates on our metal surfaces, and to identify their effect on the adhesion energy, because in some cases one could also desire to increase the adhesion of an interface. So we consider the metal interfaces that I presented before, and calculated the chemisorption of these elements of the first two periods, the non-metal elements of the first two periods, and also sulfur and phosphorus that are key elements for lubricant additives. So first of all, we identified the most favorable absorption site for these atoms by absorbing the atom in the high symmetry sites of the different considered surfaces. Then we calculated the adhesion as a function of the coverage and analyzing the chemisorption energy as a function of coverage. And finally, by mating the two covered surfaces with the selected atoms, we calculate the adhesion of the new interface and its percentual decrease or increase with respect to the clean interface. So here I report the absorption energies in EV per atom for the atomic species that I mentioned and for all the metals that we have studied before at 25% coverage. And in yellow is the corresponding equilibrium distance obtained after the relaxation. So you can see that there are, yes, atomic species that present very high absorption energy, like carbon, nitrogen, oxygen, on especially on transition metals that have the orbitals partially occupied, and a corresponding trend in the absorption distances can be observed. So again, with this high throughput screening, it's possible to, yes, obtain the, here, this is an ongoing study, so we have not yet analyzed through machine learning algorithm or general trends, but again, just with the color code that is possible to identify some relation, some correlations. We also, in this plot, I reported the adhesion energy as a function of coverage. We consider 25, 50, and 100% coverage. And we found that for almost all the absorbed species, the adhesion energy decreases as a function of coverage, as can be understood by analyzing the energy, the interaction energy between the absorbed atom that can be easily calculated by just considering the monolayer of absorbed atoms and comparing the energy per atom with the energy of the isolated atom. And we can see that apart from the very small atoms, the other atoms start to create bonds among them, increasing the coverage. And so by increasing the atom-atom interaction, we have a slight decrease of the atom-substrate interaction, resulting in a higher increase of the absorption distance and a corresponding decrease of the adhesion energy, the absorption energy. Finally, we calculate the reduction, adhesion reduction or percentage increase with respect to the adhesion of the clean metal. In this case, I'm just considering a 50% coverage. Other calculations are ongoing. And it's interesting to see that there are some elements, like, for example, sulfur, that reduces the adhesion for almost all the metals considered. And this is relevant because we know that sulfur is a key element for lubricant additives. So this kind of analysis is useful to design also lubricant additives, lubricant materials. While other elements, like, for example, carbon and the boron, instead increase the adhesion between the couple of metals considered. So if one has to increase the adhesion, for example, of a coating on a substrate, or to design an alloy with specific characteristic, this information can be useful, not just for understanding the frictional properties, but also to understand the nature of the metal-metal interaction that can be also modified by some impurities. Okay, so in conclusion, I've shown you that we developed an advanced software for performing high-throughput calculations of solid interfaces, and we applied it to describe, first of all, homogeneous interfaces, identifying general trends, and also providing a fundamental understanding on the origin of friction, for example, the relation between the interfacial properties and electronic properties. We have extended this method to heterogeneous interfaces that are more relevant for applications. And we have populated a database for metals, and also applied machine learning algorithm to be able to describe this interfacial property, the adhesion, in terms of the bulk properties and surface energy of the two separated elements. And finally, we are extending this machinery to screen how chemical surface modifications can affect adhesion. I would like to thank my collaborators that are presently working on this issue: Paolo Restuccia, Margherita Marsili, and Michele Cutini, and of course those who contributed previously to the development of the workflow: Omar Keimani, Gabriele Losi, and Michael Wallock. And I would like also to thank you for your attention.
Thank you, Clelia, for this excellent talk, for being perfect in time as well. Very nice. And with that, I want to ask the panel first, maybe, for some questions. So if we have some of the other speakers from today that want to ask some questions. Otherwise, I have a lot, of course. Because I don't think we see anything in the chat yet. So maybe I start.
No, I'm checking, and there's nothing yet, but I'm asking again.
Okay, maybe I start then, Clelia. Basically one of the last things you showed is really stark difference that you see on some of the elements for that you intercalate between the surfaces in respect to adhesion. Have you looked in if it is just could be, or some part of it could be the size of the ions? So just geometric, basically. Okay, he pushes it further apart, so the adhesion goes down.
Yes. Yes, this is related to the size of the ions. For example, I'm not able to go back. Also in the past, when we tried to study the effect of adhesion reduction in iron, we compared on the same row oxygen, sulfur, and then also selenium, that is has a larger radius than sulfur, and we found a perfect trend with the atomic radius in that case. Here it seems again that we have similar trends. We have not yet performed a quantitative analysis, but as we did for iron, as I said. But yes, in that case, it was clear that there is a higher Pauli repulsion when the atomic radius is increased, because especially at high coverage, the Pauli repulsion among between the passivated surfaces is higher when the size of the atom is higher, because there is a higher overlap of the the fully occupied atomic orbitals, let's say in this picture. So it's clear that the metal-metal interaction is better screened for higher atomic radius than for smaller one, when the separation between the surface is also not enough to prevent a direct metal-metal contact, for example, as it happened in the case of hydrogen, or even carbon or boron, that have lower atomic radius and are less effective in screening the metal-metal interactions.
Okay, yeah, makes a lot of sense. So, still no questions in the chat, I think. We actually saw that a lot of people do watch these videos later on demand, so the views go up a lot. So I will try to ask one more question. Maybe it's interesting to the future audience as well, and that is more of a technical question, maybe, because you showed that you have this quite impressive collection of software for doing these high throughput studies and to create these databases. And you also mentioned lamps and quantum espresso. I mean, these calculations I think have been done with WASP, if I'm correct. Yeah. But I know that some of these codes can expect or can use multiple calculators, let's say. But it's I think was this very hard to implement, let's say, to use, for example, lamps as well or is it possible, to do some pre-relaxation with lamps and then switch to WASP or quantum espresso for more, let's say, for the final optimization?
Okay, I have to specify that this input-output handling has been designed in general to be able to handle or automatically create the input for all the different materials. But actually, we have not yet modified, for example, the error handling, other features that are specific for the different codes. So up to now, everything is designed for WASP, and a further step, in addition to the input generation, should be carried out to make the workflow working in connection with quantum espresso, for example. But this is something that we would very much like to do, because for example, I'm using more quantum espresso than WASP, so there are users that are more familiar, for example, with quantum espresso. So we would really like to extend the work, but this is possible. It's already designed in a very general way. But some, especially for the error handling and specific features, there is still some effort to.
For sure, but I think just designing it in a way that it can be adapted is already goes very far and makes it much easier. So I see a raised hand from Martina. Please, Martina.
Hello, hi Clelia. Thanks for the talk.
Martina.
Nice seeing you. Actually, the answer to that question kind of answered a little bit what I was going to ask, but I'll ask it anyway. I was wondering if you're planning to couple to this workflow tools to do the machine learning analysis directly on the data set that you produce.
To implement algorithms such as the algorithm that I presented.
Like CISO, but that handles the data.
That is something that we hadn't planned yet, but of course could be a very good idea, because for example, this algorithm is available. So it's a Python code that can be included in our software that is based on Python. So this is something that we had not planned yet, but you are right. It could be very nice to have the final, not just the database, but also the database analysis performed automatically. Yeah.
Cool.
So maybe connecting to that, I can also say that it's of course really nice that we had last week, or not last week, but the last time we had Luca talking about CISO, and now we immediately see the application to a tribological problem, which is great, I think. And maybe in the same vein, you mentioned that it's like a lot of care has been taken to populate these databases, make them easily searchable, and so on. I think that is probably more like gives you all the tool already to then post-process this data without having to integrate everything in one complex workflow. And yeah, but I wanted to ask, because the descriptors, I mean, you talked previously, and since we work together, I'm very familiar with this about the charge density redistribution, but this was not used as a descriptor, right? In your, I mean,
on purpose,
because it's
the correlation
from the interface,
was
right?
very high, almost increases more than the values that I show, but we wanted to predict the adhesion just on the basis of the bulk properties or the surface energy of the two elemental metals. Properties that can be measured, can be found in the experiments. So this is the added value, because the charge displacement, of course, correlates very well. But it's something that, it's already an interfacial property, not a single, and it's also not directly measurable by experiment, as far as I know. So that was done on purpose, but
I just wanted to basically know if you looked at it, if you checked it out, if it would be a good correlation. But of course, I mean, I completely understand if you want to reduce the computational workload. I mean, if you calculate the charge density redistribution, you calculate the adhesion at the same time, so you don't gain any, let's say, computational advantage at least. Okay. So, do we have any more questions in the chat or in the panel? I don't think so.
Not from YouTube.
So then maybe we can already introduce our flash talks. So let me remind you again how this format works. We will now have 3 flash talks. Each will be around 10 minutes long, and we will not break for questions in between those, but we will have a 1 question and answer block at the end. So these will be a little bit less on topic, let's say, but for this high throughput and machine learning database stuff. But nevertheless, we are very happy to have our flash talkers here and to provide opportunity to speak in this format. And the first one, already I see that some cameras are getting activated. So the first one will be given by Nusrat Chowdhury. I hope I did not pronounce this too wrong, from the University of Illinois. And afterwards, I will just try to pronounce all the names now. After her, we will have a talk from Fakhrul Hasan Bhuiyan, Bhuiyan from UC Merced, also from the US. And then we have Alberto Paccini, who is actually working with Clelia at the end. So, Nusrat, if you have already unmuted yourself, if you can share your screen, she will, yes. So maybe we're a little bit early, so don't start yet. It's only at least on my clock, it's 2 minutes to 3. So I think if there's someone who is just interested in the flash talks and had not joined our YouTube stream so far, I think we should delay by 1 more minute. But it's good that you're ready. If you, I will give you a sign when it's time to start, and then I will give you also if you can make sure you have the chat open. I will give you a small reminder if I feel your time is running out, so that you can come to the conclusions in 1 or 2 minutes. Okay. I will do that in a private message in the Zoom chat. So, I think with the edit delay that we have on YouTube, now it's time to start the flash talks. So, Nusrat, please go ahead.
Yeah. Hi everyone, I'm Nusrat Chowdhury. Today I'm going to talk about neutral hydrogel permeability as a function of fluid viscosity for robust low friction application. So let's start. So what is hydrogels and why do we need hydrogels? So hydrogel is a cross-linked hydrophilic polymer that does not dissolve in water. So the potential use of hydrogels is like it can be a potential replacement for biological tissues like articular cartilage, and also it is used in contact lenses. Many researchers have tried to find the permeability of hydrogels because of the surface properties are related to the structural and chemical properties of hydrogels. So earlier researchers have tried to find internal properties like mesh size, concentration, and pore size, this type of relation with permeability. But there is not so much work on the surface properties relation with permeability. However, that is why we hypothesize that there is an explicit connection between permeability and lubrication because of the biphasic nature and low friction hydrogels. So in the current effort, we try to find the relationship of permeability with viscosity and also the relation of permeability and friction coefficients. So what is permeability? Uh, Permeability is a unit of measure that describes the mobility and ease by which fluid can navigate. So if there is a membrane, it is the measure that how much water or fluid can flow through that gel. So it, it is denoted as K on Darcy law. So there are various types of application of permeability: transport of molecular penetrance, drug delivery in biomedical and pharmaceutical companies, nanocatalysis, and lubrication mechanism. And we are trying to work on the lubrication mechanism side of the hydrogels and its permeability relation. So this is the experimental setup for our permeability tester. So the main variables where we set the pressure at varying from 10 to 30 kPa, each at 5 kPa intervals, and the viscosity of was 0.001 for a specific test. This one is water, and the gel thicknesses were 0.45 millimeter, and the hydrogel concentration of acrylamide concentration was varied from 7 to 11% for varying concentration tests. Though the setup looks very complicated, it is not. We just supplied controlled pressure through this line, and the water was flown from here to the gel holder where the gel was situated. So after flowing through this gel, the water was collected in a pot, and with time, the volume flow rate was calculated. And we measured the velocity from that volume flow rate, and with the help of Darcy law, we found the permeability of the gels. So after that, each gel was tested for 5 times at each pressure, and pressure was varied from 10 to 30 kPa for each concentration, and each concentration was tested like with 3 gels. So there was a total of 15 tests for each concentration. And from the velocity values, I showed you how we found earlier. We plotted the velocity versus pressure plots for each experiment and found the experimental permeability value with fitting this with a linear fit in the graph. And additionally, we did was applied Monte Carlo simulation, where we did uncertainty analysis for both x and y, velocity and pressure values, find ranges of x and y error bars, and applied different types, taking random values from that limits of x and y. We applied linear fit several times. For your visual clarity, I showed 5 runs of Monte Carlo simulation and their slope values and the confidence. And for reaching 95% confidence, we did 100,000 simulations of Monte Carlo simulation and find a precision up to 0.3 decimal places. So I just showed the 5 values. And moving on to the main part, and moving on with the results, we plotted total polymer concentration in the graph in the x-axis and the permeability values. So the total polymer concentration was varied from 7.45% to 11.45%, keeping the monomer by crosslinker ratio constant at 25. So the main takeaway of this graph is like the permeability has a definite concentration that does not vary much, and with increasing concentration, with increasing monomer and crosslinker concentration, the permeability is decreasing. Why is that? The higher the monomer crosslinker concentration, the higher the polymer chains will be closer to each other, and it will be hard for the fluid to flow through that gel. So that is why the permeability decreases with the monomer and crosslinker concentration. So another takeaway of this graph is that with a very few experimental values, we can get more precise Multicolor simulation prediction and get a more precise permeability values. And also we can predict that permeability values from the Multicolor simulation, and the concentration we tested also at different concentration, we can predict the permeability. So, and moving on to viscosity relationship with permeability. So one of the papers from our lab found that there is a surface property friction coefficient have a relationship with permeability and viscosity. So in the relationship, you can see the friction coefficient has relation with permeability and viscosity. So there is also, so in the graph also, this graph is from the paper. So the friction coefficient versus speed into viscosity has a like a lubrication regime. And so we are assuming there is some friction underlying mechanism working on it. So as the Darcy law has also relationship with permeability and viscosity. That is why we are trying to find viscosity relationship with permeability. So for this, we are using DMSO in our experiment. We just use the same experimental setup, but substituted water with DMSO now. And the viscosity of the fluid was varied by varying the concentration of DMSO in water. So the experiments are ongoing. We hope to find some valuable findings from these results and present you in future. And moving on to the friction coefficient relationship with permeability. So in a past paper from our group by Real, friction was shown to have control by how much water is in the gel in the area of contact. So that is why we are predicting that permeability is an important parameter in defining friction coefficient. So in the graph, you can show that, see that friction coefficient and versus Peclet number is shown. So what is Peclet number? Peclet number is a ratio of advection by diffusion. So the higher the diffusion, the higher the Peclet number will be. So in the graph, they found that with higher Peclet numbers, the friction coefficient decreases. So we are predicting that there would be some relationship of permeability and friction coefficient. As you can see from the equation, the permeability is a direct parameter of Peclet number. So these experiments are also ongoing, but we hope to find a direct relationship of permeability and friction coefficient in future. Thank you. Let me know if you have any questions.
So thanks for the first presentation. Questions, as I said, will be done afterwards. So with that, I would ask Fokrul to share his screen, please. Okay, and please go ahead with your presentation.
I hope you can see my screen.
Yes, we can see it well. We can see you. We can hear you. Maybe you can just start. We are perfectly in time.
Okay, sure. Got it. Nice. Hello, everyone. I'm Bhuiyan, a fourth-year PhD student in the Martini Research Group at University of California, Merced. Today, I'll be talking about our study on tribochemical reactions of simple organic molecules at a sliding interface using reactive molecular dynamic simulations. Recently, it has been shown that many application-relevant tribochemical reactions are assisted or driven by mechanical stresses available at a sliding interface. But how do mechanical stresses drive such reactions, and what are the molecular mechanisms? Here, today, I'll try to answer these questions, but first, let's start with tribochemical reactions. Well, as you may know, almost all tribological systems involve some chemical reactions that are commonly known as tribochemical reactions. These reactions can be association or dissociation of these interfacial molecules, or reactions between these molecules and the surfaces. Such tribochemical reactions can lead to either material removal or wear, or material accumulation, such as tribofilm formation. And many of these reactions, in fact, do not happen naturally without the application of sliding motion. Tribofilm formation specifically has been shown to be driven by mechanical stresses. And tribofilm is critically important for the efficient function and durability of machine components because tribofilm reduces wear and friction, especially in the boundary lubrication regime. But what is the tribofilm? Lubricants, among many other additive molecules, contain small amount of anti-wear additive molecules such as ZDDP, TCP, or MODTC. During operation, these additives can react with the surfaces of the machine components and create a protective film on the surfaces. This protective film, which is also known as tribofilm, reduces friction and wear by minimizing solid-solid contact. So from no film to tribofilm growth, tribofilm forms through some mechanism. Three key components of film formation are the physical and chemical composition of a tribofilm, the reaction mechanisms that lead to that film growth, and how different operating conditions such as heat or stress affect these film forming reactions. To fully understand tribofilm formation, we have to discern the individual contributions of all three components. And for that, we have several research tools available at our disposal, such as theoretical framework to model film forming reactions or different experimental techniques in macro scale and nanoscale to study film growth. Although these research tools have done a great job to elucidate these mechanisms, there are some key questions that still needs answering. For example, how heat, pressure, or drive tribofilm formation, and what are the differences between the shear-driven pathways or mechanical reaction pathway and the thermally driven reaction pathways? What's the difference between the contribution of normal stress versus shear stress? And how does molecular structure affect susceptibility to mechanochemical activation? We believe that computational techniques such as molecular dynamic simulation is a powerful tool that can be effectively used to complement the theoretical framework and the experiments to fill in the blanks. As such, we used molecular dynamic simulation with reactive force field to simulate alpha-pinene molecule in between two silica slabs. Reactive force field can capture chemical association and formation, which allows us to study the chemical reactions happening at an interface. We performed three types of simulations: a heating simulation, a compression simulation, and a sliding simulation. We then tracked the chemical reactions that happened in these systems. The two key reactions that we looked at are oxidative chemisorption and oligomerization. For the oxidative chemisorption reaction, you can see an alpha-pinene molecule reacts with a surface oxygen atom to become oxidized. And for an oligomerization, two alpha-pinene molecules react with each other to form an oligomer or dimer. And as you can see, in both cases, the surface oxygen atoms or the surface plays a key role in these reactions. Interestingly, we observed that the oligomers formed at high temperature in heating simulations formed at very high temperatures, and no oligomers formed in just by compression. However, significant number of reactions happened in the sliding simulations at room temperature. This means that shear is a key driver of these tribochemical reactions. We then analyzed the reaction pathways that led to oligomer formation and found multiple such pathways. In pathway A, the double bond side of both reactant molecules were activated to form the dimer. On the other hand, in reaction pathway B, the four-membered ring was activated which then got oxidized and then reacted with a similar molecule to form an oligomer. Interestingly, both pathways were accessible through shear stress or mechanically, but only reaction pathway B could be activated thermally. This suggests that the mechanical stress-driven pathway and the thermal reaction pathway of the same reaction can be different. This also suggests that the chemical features of a reactant can play an important role in the mechanical activation. To further understand the effect of different chemical features of a reactant in their mechanochemical activation, we simulated three simple organic molecules: methyl cyclopentane, which has a methyl group side chain; cyclohexane, which is a 6-carbon cyclic molecule; and cyclohexene, which is like cyclohexane but has a double bond. We compressed and sheared this molecule at a silica-silica interface and then tracked the oxidative chemisorption reactions. In this molecule versus simulation time plot, the darker blue represent the change in the number of precursor molecules in the simulation, and the lighter blue represents the oxidized molecule in the system. And as you can see, methyl cyclopentane and cyclohexane were not that sensitive to mechanical stress as they remained fairly unreactive. However, cyclohexene was very sensitive to shear stress as it reacted vigorously as soon as we started the sliding process. But what is causing this significant difference among these molecules? To answer that question, we numbered the carbon atoms of the molecules from 1 through 6 and calculated the probability of each of these carbon sites to participate in an oxidation reaction. The result is shown as a pie chart. Looking at methyl cyclopentane and cyclohexane, it looks like all carbon sites of the two molecules were more or less similarly reactive, as they have similar probabilities of going through an oxidation reaction. However, cyclohexene is completely, again, different, as most of the oxidations happened at the double bond site, which is the C1 and C2. This suggests that the carbon-carbon double bond is more susceptible to mechanical stress. We also looked at the number of oligomers formed in our system and found that cyclohexene formed the highest amount of oligomers, while the other two formed only a few oligomers. Since oligomers are the first step towards tribopolymerization, we compared our results to ball-on-flat tribometer experimental results of these precursor molecules, and we found a qualitative match. Since cyclohexene also produced in the experiments the highest amount of tribopolymers. And finally, we analyzed the oligomerization reaction pathways and found out that methyl cyclopentane and cyclohexane followed a similar reaction pathway that involved hydrogen elimination, then oxidation, and finally oligomerization. Cyclohexane followed a slightly different path, which involved direct oxidation at the double bond site, followed by oligomerization. In conclusion, we observed that tribochemical reactions can be driven by mechanical stress, and these type of reactions are also known as mechanochemical reactions. By modeling such reactions using reactive in the simulation, we tried to capture the atomistic details of mechanical activation of these molecules. Our simulations enabled the isolation of the effect of heat, normal stress, and shear stress. And we found that shear stress to be critical in driving these reactions. We systematically studied different organic molecules to capture the effect of different chemical features on mechanical activation and found out that carbon-carbon double bond can be quite susceptible to shear stress. That's it. The main point, the takeaway point is that simulations can show how chemical structure affects the mechanism of and susceptibility to mechanical activation. With this, I'd like to thank you all. And this is a published work that you can find here. Thank you.
Thank you very much. Very nice talk. Again, questions will be asked later. So please, Alberto, if you can share your screen now.
Share the screen. Okay. Okay.
Perfect.
Okay.
And we are still perfectly in time.
Okay. Welcome, everyone. I'm Alberto Paccini, working at Clelia Righi's group at the University of Bologna, together with Gabriele Losi, the previous member of the group, and in collaboration with Nobuaki Kitawa and Seiji Kajita at the Toyota Center Lab in Japan. And we developed a new multi-scale method which links together ab initio and Green's function molecular dynamics, and we applied it to study diamond interfaces. I would like to recap ab initio molecular dynamics. So we start with an atomic configuration, then we have to solve the Concham equation for the electrons. We find the electron density, which in turn gives us the force that acts on the nuclei. And then upon integrating this equation, we get the new nuclear configurations, and updating that, this is a classical, let's say, ab initio molecular dynamics loop. So we have described what is called the Born-Oppenheimer molecular dynamics. The problem is that this equation has to be solved at every iteration, so it's computationally expensive. Another approach is the Parnell molecular dynamics. This equation is just solved at the beginning, and then the orbitals are just propagated in time together with the nuclear coordinates. So it's much faster. Now, in our case, we want to study sliding interfaces. So this sliding induces vibrations at the interface that then propagates into the bulk. And in order to capture this vibration, one needs a large number of atoms. And this is a problem with ab initio molecular dynamics because it scales with the number of atoms. And so we rely on multi-scale approaches. And the idea of multi-scale approach is very simple. We divide our system in two parts, one chemically active and one that acts like a reservoir region, which is simulated classically. Now, in our case, this splitting is quite natural. So the interfacial atoms will be simulated ab initio, and the bulk atoms will be simulated classically. But then we want to simulate actually a semi-infinite bulk. And this is a problem also for classical molecular dynamics because we have an infinite number of atoms. So we rely on the Green's function approach, first devised by Martin User. And the idea is to use this Green function to project the dynamical response of an infinite number of atoms onto a Green function atomic layer. And this is, let's say, a convolution integral which exploit this Green function and give us the response of the bulk atoms. Now, to intuitively understand what is the Green function, so let's imagine to poke a system with an external force. This force will propagate inside the material and displace atoms in a complicated way. But this is governed by the internal dynamics of the system. And the Green function can be seen as a response function which links the input, which in our case is the forces that the quantum mechanical atoms at the interface apply upon the bulk atoms, and the response, the output, which is the bulk atoms displacement. Upon some approximation, we can derive an equation that the Green function has to satisfy, which depends on some parameter of the bulk, which are elastic parameter of the bulk, which can be calculated via ab initio Phonon calculation. We can overview the method in brief. So we start with a bulk. We perform phonon calculation to get the internal force matrix, which allows to, let's say, to get an equation for the Green function, which is then computed, and then we can use it inside a standard molecular dynamics loop. And the idea is just that instead of directly evolving in time the quantum mechanical atoms, we first perform the convolution integrals to take into account also the dynamics of the Green function atoms. We apply our setups, our GFCP molecular dynamics, to study diamond interfaces with different degrees of passivation under tribological conditions. And what we observe is that at zero coverage, we have a graphitic layer, which is formed at the interface. With 25% coverage, the system remains stuck, so it doesn't not slide for the applied lateral shear. Whereas for the 50%, 75%, and full coverage, we have sliding, and we focused on the dynamics of these systems. So we report the time average of the derived from the dynamical results for these three systems. So we applied first 1 gigapascal of lateral shear. This gives rise to these sliding velocities, but the important fact here are the friction forces, which shows a decreasing trend with increasing hydrogen passivation. So, and also this is reflected in the kinetic friction coefficient. Then we repeat the same analysis also for 5 gigapascal of applied lateral shear. Now the velocity is increased also almost to 300 meters per second. And we see an interesting behavior of the friction force, which for the, let's say, systems which possess the most coverage of hydrogen, we have the friction force which decrease with the lateral velocity, with the applied shear. And we want to further investigate this fact. So what we have done is we take our interface and we perform static calculation to get an adhesion energy map. And we know that the minimum energy path is a property of the potential energy surface. And then we start the lateral shear, and we record the relative trajectories upon the potential energy surface for both the sliding regimes. And we perform this analysis for every passivations, and we get these beautiful plots. And we can see that at the low applied shear, the systems tries to follow the minimum energy path. Whereas for higher applied shear, the system, actually the trajectories do not resemble the minimum energy path. It's much straighter. So we know that the potential energy surface induces forces by taking just the gradient of the potential energy surface, and we project those forces along the trajectory. So we perform this projection for the 1 gigapascal shear, and we get this graph. So we can recognize this characteristic sawtooth profile, which is characteristic of stick slip regime, in which we have a stick phase where an accumulation of elastic energy is occurring. And then we have a slip phase where this elastic energy is released. And through phononic dissipation, we lose, let's say, energy, kinetic energy, and we get a net friction force, which is indicated by this average here. Then we repeat the same procedure for 5 gigapascal of applied shear. And we see that in this case, we are in a continuous regime where there is an efficient force compensation because the systems are sliding over the potential energy surface and are not very affected by them. And there is an higher cancellation, and so a smaller net friction force. Then this is the real, let's say, forces coming from the dynamical simulations. And this is a very noisy signal because of thermal fluctuations. So we perform a Fourier transform, and we analyze the low frequency region of the spectra. Why we do that? Because we know that there is a relevant frequency, which is called the Washburn frequency, which is given by the sliding velocity over the lattice constant. And in our case, we see that at those Washburn frequency, the spectra for the real dynamical forces are peaked and are similar to the past-derived forces, which are peaked at the Washburn frequency. And furthermore, we see that there are all those peaks at higher frequency, which are related to surface modes because are common to every system, whereas at low frequency, we have interfacial modes which characterize the different passivations. So in conclusion, we developed a multi-scale method which links ab initio and Green's function molecular dynamics, which takes into account both electronics and phononic degrees of freedom. And so this gave us the possibility to obtain quantitative estimates of kinetic friction coefficients, which are in agreement with experiments, and also describes known tribological phenomena like effect of surface passivation and graphitization, and also to gain insight into the fundamental nature of friction. Thank you very much for your attention. If there are any questions,
thank you, Alberto, for this nice presentation. Also nearly perfectly in time.
Thank you.
So now, I think if you stop sharing, we can maybe see everybody again, at least the faces. And this time we have already some questions in the chat. So very nice that apparently the audience is much more interested in the flash talks than nothing against the wonderful presentation of Clelia, of course. So the first question that we got is from Stefan Peters, which is for Foucault. So second presentation. What is your opinion, the reason why shear is able to promote the reactivity of the molecules while load and temperature do not promote those? Or not in the same sense, I imagine.
Yeah, that is a great question, actually. And that is something that we're pursuing right now. From our previous studies, we have seen that shear stresses can deform molecules. So they can induce deformation of the molecules just before a reaction happens. And based on that result, we kind of suggest that maybe shear stress induced deformation make the molecules reactive. But that also, then the next question would be, why can compressive stress do the same thing? That right now I don't have a good answer to, but we have seen that compressive stress cannot really deform a molecule. Why not? I'm really not sure at this point, but yes, that's an ongoing investigation.
Okay, thank you. So second question is actually also for you. It's from Davide Sarpa. I hope I pronounced that correct. So, hello, amazing talks everyone. I wanted to ask Foucault if they tested the effects of film thickness on the promotion or demotion of chemical reactions.
Film thickness, we have not done that kind of study yet. Mostly we try to stay close to our experimental collaborators who are doing vapor phase lubrication condition experiments. In that cases, we expect a monolayer film thickness on the flat. So in simulations, we also try to simulate a monolayer film, but definitely we are interested to do thickness-based experiments and also changing the shear rate or sliding speed, the effect of shear rate or sliding speed in these reactions. That would be also interesting.
Okay. So then we have another question by Stefan, here. What is the effect of oxidation clusterization of the compounds on the tribological properties of the interfaces? Are they useful or not? So this is again for you.
Can you say that again, please? Sorry.
Okay. What is the effect of oxidation/clusterization of the compounds on the tribological properties of the interface?
tribological properties. I think that's an interesting question. So from our results, we found that the oxidation is important to drive this tribochemical reaction. So to drive the tribopolymerization. We do not see tribopolymerization, but we see oligomerization in the simulation. But in the experiments, they see tribopolymerization, but they cannot see any process what's leading to that tribopolymerization. So based on the experimental result and the computational result, we suggest that these oxidation reactions eventually lead to tribopolymerization. So, they play an important role. But again, the oxidation, happens through surface oxygen atoms and the precursor molecules. So precursor molecules are reacting with the surface oxygen atoms, and during the sliding process, they can take that oxygen molecule with them from the surface, and that can lead to wear. And we have seen that in the experiments. So that also, through the simulation, we kind of found the wear mechanisms of that they see in the experiment. So yeah, that oxidation can also lead to wear.
Okay, thank you. I have a question, although probably not a very intelligent one for Nusrat, because I had really, this is really not my expertise, but you had in the beginning these lovely pictures of knees, and my knees are really bad. And I was interested in if this hydrogel research that you do, I mean, how many years is this away for actual this application of cartilage in knees, of artificial cartilage maybe, because for me this will be very important in 10 to 20 years, I imagine.
Yeah, so there are various types of properties. So we know all work, friction and lubrication and wear of this gels. So we are doing some tests to see how biodegradable it is. So whether the permeability is changing with time or not. So far my gels are not changing with time, the permeability. So that's one type of findings we are doing. And also whether the friction matches, and so the lower the concentrations, the friction is lower, but when the concentration is higher, the frictions are higher. But in our articular cartilage, the stiffness is also higher and the friction is also lower. So we are trying to replicate that type of things, which are very hard in real life, but it's presumably possible with hydrogels. That's why. So yeah, I think it will take 10 to 15 years, and we are close to it almost. Yeah.
I think 10 to 15 years is for me a satisfactory time frame. That's my doctors give me that at least, yeah. Okay, thank you. Then maybe I don't see, I mean, if there is anything else in the panel, anyone wants to ask a question?
Hey, sorry, my internet connection went down and I lost a couple of minutes. I had a couple of questions if we have time.
I think so, yes.
We don't have more questions in the chat, which I don't think we do. So my first question was for Fakhro. So you mentioned you did shear simulations as well. How did you decide which velocity to choose? And as you also mentioned you use the Reactive as a potential. Is there a problem with choosing given a shear velocity when you use Reactive as a potential?
Yes, thank you, Stella. That's a good question. The shearing rate, or the sliding velocity that we used was 5 meters per second. That's usually, a common value to use in this type of molecular dynamics simulation. That's if we convert it to something experimental or experimentally relevant number, then that would be actually a pretty high value, pretty high sliding speed. But due to the computational cost and resources that we have to run at these type of values. And using Reactive, we haven't really seen any problems, I guess, with different sliding speeds or shear rates. Definitely a lower sliding speed would be, better, but I guess we can, I have seen even people using 10, 20 meter per second, and that was acceptable. So I haven't seen any problems in my experience yet.
Okay, thanks.
Thank you.
Last curiosity was for Alberto, but I don't know whether you guys have already asked something because I went down for like 2 minutes. I don't know what happened. I was just curious in which framework combination of codes and methods you have developed your multi-scale approach.
So the Carparinello is within the Quantum Espresso suite. And then there is, say, a preliminary part, which is written in Ruby, which basically takes into account the calculation of the green function, starting from the phonon calculation, always performed within Quantum Espresso. And then there is actually the link, which is written in Fortran, so is compatible with Quantum Espresso, which basically links, let's say, the pieces, and it is within the module in molecular dynamics of Carparinello.
Okay.
So it's Carparinello and let's say a Ruby external package.
Wrapper.
Yeah. Called
Okay.
Green Tea.
Okay. Cool. Thank you very much.
You're welcome.
So maybe I have not really a question, but kind of discussion opportunity maybe within the panel, because I'm not really a molecular dynamics guy myself, but I would be interested in a discussion between Alberto or some comments by Alberto and Foucault about different ways of running this. Like this, as far as I understood, this Green's function method kind of alleviates the use of a thermostat. Or
yes.
Yes. So maybe you can comment on the advantages of using more traditional methods to thermostat a system like this, tribological systems, or the advantages of doing this with this green function method. So
yes.
yeah,
So
I would love to have comments by both of you on this. Thank you.
Yeah. So let's say the thermostat are present within the let's say the bulk region. So they are taken into account by the green function atoms. And the way to do that is basically to initialize the velocity of the bulk atoms in such a way to be compatible with the temperature that you want. And then also the green function takes into account the shear, for example, and the applied load. So basically, you set the thermal conditions and the barostat by setting the initial condition for the green function atoms, which are subjected to an harmonic dynamics. So basically, there is a dynamics which takes into account the response that they have to do with respect to the interfacial region. And there is a free dynamics which takes into account the initial conditions and gives you the opportunity to set the thermostat and bars. So basically, it's within the green function. So the interfacial atoms are not thermalized. I mean, they are thermalized because of the interaction with the green function atom, which represent the bulk.
Okay, that's nice. I can say from my perspective, the way we thermostat our system is probably somewhat, I don't know, can be different, because usually, as Alberto said, thermostats are done at the bulk or at the surfaces. In our shear or sliding simulations, if we want keep the temperature constant, we have to thermostat the molecules too. Otherwise, because in the experiments, they can calculate the increase in temperature, flash temperature at the interface, and in their cases, the increase in temperature is quite negligible. So in our system, we try to do that by thermostating the molecules, the interfacial molecules themselves, to so that during the sliding process, that temperatures don't fluctuate too much or increase too much due to the sliding process.
Yeah, so yeah, as I said, in our case, you basically leave the interfacial region without the thermostat, and during sliding, clearly you have energy dissipation into the interfacial region, which is then transported away from the interface through the bulk, and
Yes,
this is
yeah,
done
definitely.
with the coupling of the green
Mhm.
fan. And clearly, this effect of the thermalization is kind of physical because you are effectively simulated an harmonic bulk. So you take into account the effect of thermalization in an harmonic way. So say a first order approximation, okay, of something which has to be.
Okay, thanks. With that, I think we have taken our time that was allotted for questions. We have, if somebody has more, we can do that. We have scheduled a 50-minute break, however, which I kind of have to use to go to the bathroom. So if there are no more questions, I think we keep the string going. So also you will be able to post some more questions in the chat, so we could do also some more questions for the flash talks or for Clelia after the last talk, which will come up on the full hour at 4 in the afternoon Central European time. Yeah, so with that, maybe we can all give a virtual applause to the speakers of the first of the flash talks and to Clelia. And yeah, then I see you in a couple minutes when we resume the stream with Noah and the last invited talk of this session.
See you in a
Thank
bit,
you.
everyone. Thanks again to all the speakers.
Thank you.
Thank you.
Bye bye.
See you.
So I can see Noah as well because I couldn't so far.
I have to turn my mic up as well. Okay, so now everybody should hear me again, and maybe I hope the others as well. And I have the pleasure to introduce our final speaker for today, which is Marom. She is an associate professor at the Material Science and Engineering Department at the Carnegie Mellon University in the US, where she and her group combine quantum mechanical simulations with machine learning and optimization algorithms to computationally discover and design materials with desired properties for various applications. From 2013 to 2016, she was an assistant professor at Tulane University after a postdoc at the University of Austin. She is a member of the Pittsburgh Quantum Institute and affiliate of the Scott Institute for Energy Innovations. Professor Marom has received numerous awards after her PhD in chemistry, which she received at the Weizmann Institute of Science in Rehovot, Israel, for which she also received an award, which include the most recently the Dean's Early Career Fellowship from the CMU College of Engineering and the OpenEye Outstanding Junior Faculty Award for the Computers in Chemistry Division of the American Chemical Society. Her research interests, while not centered on tribology directly, are very broad, from materials for quantum computing and organic solar cells to molecular crystals. Today, we will hear her talk about interface modeling, which connects very well to Clelia's talk earlier, and implying several modes for machine learning and Bayesian optimization and so on. With that, I invite Noah to share her screen and have fun with the presentation. She reminded me just in the break that if you want to ask questions during the talk, please feel free to do so. I will relay them to her and we can keep this a little bit more interactive. So Noah, please, you can start.
Okay, thanks for having me here. So the topic of my talk today is first principle simulations of hybrid interfaces. And what do I mean when I say hybrid interface? That means an interface between dissimilar materials, like a semiconductor and a magnetic material, or a semiconductor and a superconductor. And the nice thing about these interfaces is that when you put these materials together, you can get physical properties and functionalities that you can't get out of any of these materials separately. So having an interface between two materials allows you to achieve unique functionalities. For example, at the interface between a ferromagnet and a semiconductor, you can get, I'm sorry, my cats are fighting in the background. So at this interface, you can get spin injection from a ferromagnet into a semiconductor, and that can enable the implementation of spintronic devices. And then the superconductor semiconductor interfaces are of interest currently for the potential realization of quantum bits based on Majorana fermions. So that's the motivation for studying some of these interfaces. And of course, there are many other interfaces that are of interest for various purposes. And our goal is to develop general purpose computational tools for simulations of interfaces, which includes predicting the structure of interfaces and also their electronic and magnetic properties. And why are computer simulations useful? First, they can help interpret experiments. For example, if you have a spectroscopy experiment, it can help assign spectral features to specific structural features. And then another useful thing is, the space of materials that you can use to make interfaces is very large. And so we can many possible interfaces. So with simulations, we can help experimentalists determine which interfaces might be worth pursuing. So with that said, I'm going to start by telling you about how we predict the structure of epitaxial inorganic interfaces. So, so sometimes, or in many cases, epitaxy is between two materials that are lattice matched, and their lattice parameters are very close. And then the film will just grow continuously on the substrate. But you can also have domain matched epitaxy between two materials whose lattice parameters are mismatched if you have supercells with integer numbers of cells of each material that form a commensurate interface. And there's an algorithm called the Zurn-McGill algorithm that can help you find commensurate supercells within a given mismatch and area tolerance. And we implemented this algorithm. So here you can see the results of a Miller index scan of the interface between aluminum and indium arsenide. And what that does is it goes through all the combinations of Miller indices of substrate and film, and it'll find all the possible domain matched interfaces within your misfit tolerance and area tolerance. So as you can see here, you get a very large number of candidate interfaces with these tolerances, 116 domain matched structures. And this graph here shows you the lowest area misfit for each combination of substrate and film Miller indices. And you can see here that 3 combinations are the best. We have 111, 111, and then aluminum 011 on indium arsenide 111, and 012 for both combinations. So 012 is not, it's a somewhat higher Miller index, so it's not something that's typically used. So we're going to go with the 111 substrate. And then of these 2 interfaces, the 111 on top of 111 has a slightly lower misfit. So it's somewhat more likely, and we're going to focus on this one. So what we do next is what we call surface matching. So even if you have a domain matched, lattice matched interface, there's still the question of the interfacial distance in the z direction between the substrate and film, and also the in-plane registry between the substrate and film that need to be optimized. And it's better if you can do that with some low-cost computational method. So to this end, we developed a geometric score function that is based on the overlap and empty space between atomic spheres at the interface. So it's purely geometric. And the overlap term is here, it's squared, and then it's kind of an effective repulsion term. And the empty space here has the C parameter in front of it. And the C parameter is a system-specific parameter that we can also determine without any input from first principle simulations. So our experience has shown empirically that when the Okay, let me start the story from here. So here you can see the z distance curves, and the dashed line here is the density functional theory reference. And then all these different curves in different colors are the score function curves that you get with different C parameters. So you can see that the C parameter significantly affects the shape of the curve. And we define delta S 0, that's when C is equal to 0, is this distance here. And then delta S of C is this distance here. And we find empirically that when the ratio of these two distances is equal to 0.1, you get the best agreement with DFT and the position of the minimum. This is an example for tin telluride, calcium telluride interface that you can see here. So with that C parameter, you can see here that the score function is in very good agreement with the density functional theory reference, and it gets the positions of the extrema, the minima, and the maxima correctly, which is pretty good considering that there's no quantum mechanical information going into this score function. So after we do lattice matching and then we do surface matching for all the lattice matched candidates, we have to rank the resulting interfaces in order of stability. So in principle, you could do that with DFT. And we have the definition here of the interface energy, which is the energy that it takes to eliminate two surfaces and create the interface. So we have the two surface energy contributions here, and then you have the adhesion energy between the substrate and film at the interface. And the adhesion energy is defined as the energy of the isolated substrate plus the energy of the isolated film minus the energy of the interface, where all of these are DFT total energies, and they're divided by the interface area. So this interface energy has to be converged with respect to the number of film and substrate layers. And the reason is that you need the number of layers to kind of approach the bulk limit in order to get the asymptotic value of the interface energy. So here you can see for the aluminum indium arsenide 111 interface, the red curve is when we change the number of substrate layers and keep the film layers fixed. And the blue curve is when we change the number of film layers and keep the substrate layers fixed. And this dashed line is the average, and you can see that ultimately they go to the same converged value. So this you can calculate, but it's a pretty computationally intense calculation because of the fact that you have to converge the number of layers, and you end up doing pretty large calculations. So is there a quicker way of getting a rough estimate for relative stability as well? For this, we have a ranking geometric score function that's based on the overlap between atomic spheres, where we compare the overlap of spheres at the interface with an overlap of spheres in a purely film slab. That's illustrated here. We take these three layers and we look at what happens at the interface compared to what happens in the pure substrate. And then we do the same for the film, what happens at the interface compared to the pure film material. And the idea is that the smaller these differences are, the more similar the interface environment is to the bulk environment of this material. And so that would make for a more stable interface. So again, a pretty simple, kind of simple-minded geometric idea, but you can see that we get a ranking that's in agreement with the DFT ranking, which is pretty good for a crude geometric model. So when we get to this point, we see that the interface that's ranked as the most stable using the score function and DFT is in agreement with the interface that's observed experimentally in high resolution TEM. And so that shows you that we can predict the structure of ideal domain-matched epitaxial interfaces by lattice and surface matching. So are there any questions on this part of the talk before I move on?
Maybe I can ask a question. Or there's someone else as well?
Sure. No, that was me. Just saying that there's nothing in the chat so far. But please, go on. Yeah. Ask a
Just
question.
a curiosity. Have you noticed any sensitivity of DFT to the ranking, depending on functional spaces?
So we haven't tested different functionals for the ranking. And actually, that's a good lead question for the next thing I'm going to talk about.
Cool.
So because of the computational cost of these simulations, we can only calculate these interfaces with semi-local DFT or DFT plus U, and what we use is DFT plus U, which brings me to the next topic.
Maybe I can interject and ask also a small question.
Thanks.
On one of the previous slides, you had an interface composed of one, I think, aluminium, and the other one was, I guess, also this indium arsenide. So how, I didn't know if you mentioned it, but I didn't get it at least. If you have a surface of one of the crystals or one of the slabs, let's say that has two different possible terminations, would that be?
Yeah.
So how do you deal with that?
So in this case, we knew what termination they had in the experiment. They had arsenic terminated substrate, so we used arsenic termination. But if you don't know the termination, then you can do both of them.
Makes perfect sense, of course. Thank you. So that will be also possible in the code. It will just check both. Or,
yeah, and you'll have to check both, and your C parameter will be different for each one.
Yeah.
Okay. So now that we have the structure of the interface, we want to study its electronic properties by the DFT plus U method, which I'm going to describe momentarily. And we machine learn the value of U for each material. So I'll start by explaining a little bit about density functional theory. That's the method we use to calculate electronic properties of materials and interfaces. And the idea of density functional theory is that you can use the electron density as the basic variable instead of the many-body wave function. And intuitively, it makes sense because the density is actually an observable that you can measure in an experiment, whereas the many-body wave function is not an observable. So what guarantees that we can do that, use the density instead of the many-body wave function, is a theorem called the Hohenberg-Kohn theorem, which proves the one-to-one correspondence between the electron density, the external potential, and the many-body wave function. And the reason why this is so good is that the many-body wave function is a bit of a monstrosity. It's a function of 3n spatial coordinates, where n is the number of electrons, which can be very, very large, even in a small system. Whereas the electron density is a function of 3 spatial coordinates. So you can go from 3 n variables to 3 variables with no loss of information. And now we need a way of finding the ground state density. And for this, we have an equation called the Concham equation. That's the basic equation of DFT. And it describes a mapping of the many-body problem onto an effective single particle problem, which results in this eigenvalue equation with this effective Hamiltonian, where you have the kinetic energy, the potential of the nuclei, the electrostatic interaction between electrons, and then there's this exchange correlation potential where all the many-body effects are buried. And you can see here that the Hamiltonian actually depends on the density. So you have to solve this equation self-consistently. You diagonalize, get a set of eigenvalues and eigenfunctions, construct the density, plug it back in, and so on until you reach convergence. So the only problem is this exchange correlation functional is not known exactly, and so it has to be approximated. And this is why DFT is exact in principle, but approximate in practice. So that brings me to the next point, which is in order to solve the Concham equation, you have to discretize it in a basis. And a lot of DFT codes use a plane wave basis set, which is a very convenient choice for periodic solids. However, an interface doesn't have a 3D periodicity. And so in order to deal with that, we have to, first of all, make sure that our interface model is commensurate in the XY plane, which may require a large supercell in the XY plane. And then we have to make sure that we have enough layers of each material to avoid quantum confinement effects and reach the bulk limit, which makes the simulation even larger. And then if we want to simulate a surface, then we have to add vacuum space to our model in order to avoid interactions between periodic replicas in the z direction, which makes it larger still. And then finally, if we want to eliminate spurious states from dangling bonds, we also need to passivate the surface with pseudo-hydrogens. So that means that simulations of interfaces can be technically involved and computationally expensive just because the interface model ends up being very large. So within DFT, we have different approximations for the exchange correlation functional. And one of the most popular approximations is the PBE generalized gradient approximation. And the reason it's popular is that it's very computationally efficient because of its locality. However, the problem with it is that it suffers from a problem called the self-interaction error, which is a spurious repulsion of an electron from itself. And as a result of that, the band gaps of materials tend to be underestimated, sometimes to the point that a narrow gap semiconductor like indium arsenide will turn into a metal. And this is what you can see here. There's no gap here. And so that's pretty bad news for indium arsenide. So there are more accurate approximations called hybrid functionals. And the reason they're called hybrid is that some fraction of exact exchange is mixed with the semi-local exchange and correlation. The problem with the exact exchange is that it's a non-local operator, and so it's an order of magnitude more expensive to calculate. So you can see here for indium arsenide, the HC hybrid functional does produce a band gap, and that's good. However, its computational cost is so high that we can't use it for these large interface model that we actually want to calculate. So that's a problem. And the compromise is what we call DFT plus U, where a Hubbard U term is added to the DFT energy for certain orbitals to correct the self-interaction error. And we have an effective U parameter that is the difference between the on-site Coulomb repulsion U and the exchange interaction J. And so that's being added to the DFT total energy. And the advantage of this is that it has the same computational cost as semi-local DFT. The problem with it is that now you have this effective U parameter, and it's a system-dependent parameter, and you have to figure out what value of U to use. And in order to determine the value of U that we want to use, we developed this method of machine learning U by Bayesian optimization. So Bayesian optimization is an algorithm for finding the extremum of what we call a black box function. So you don't know the form of the function, and you want to find its optimum with a minimal number of function queries. So you know what the function value is in a few points, and then you build a surrogate model to guess the form of the function based on the points that you do know. So we, in order to perform Bayesian optimization, we have to define the objective function that's being optimized. And we define an objective function that is meant to reproduce the HSE band structure and band gap as closely as possible with PBE plus U. So it has two terms. One term is just the difference between the band gaps, and the other term is what we call delta band. And this is the qualitative features of the band structures. So we take the difference between the energy, the band energy of HSE and PBE plus U at every point in the band structure, and we shift both the top of the valence band and the bottom of the conduction band to 0 in order to eliminate the effect of the gap and just consider the qualitative features of the band structure. And we sum over a chosen number of bands, and then we sum over all the K points in each band and divide by the normalized by the total number of energies we sample. So that's delta band. And alpha 1 and alpha 2 can give different weights to these two terms. So let's see how this works for indium arsenide. So the Bayesian optimization has the Gaussian process predicted mean, which is our guess of what the objective function looks like. And then we have an acquisition function, which determines where to sample the next points. So you can see that in the beginning, you kind of sample randomly, and we have like no idea what the objective function looks like. But after several iterations, it converges to this region. In the optimization, and this is a 2D optimization to find the U parameters for the p orbitals of indium and arsenic. And in the end, this is the PBE plus U BO band structure, and this is the HC band structure. And you can see that we have a similar band structure and we have a band gap, which is good. So now we can go ahead and simulate interfaces with indium arsenide. Okay, So any questions on this before I move on to some applications?
I see a question in the chat.
I think that was actually related more to the last part, so maybe we should put it in the end. I have a question
Okay.
to this part actually.
Yeah.
So how do you select the orbitals if you I mean, of course, the intuition that you know, like as a chemist, of course you know which orbitals to select, but have you automated this in some way that that for example, if you have a material that contains 3 different species, you will like optimize like d orbitals for this and p orbitals for that, and yeah.
Yeah, so we can project the band structure on the different orbitals to see the contributions of different orbitals. So so you can see here, for example, that the arsenic p orbitals and the indium p orbitals contribute here to the top of the valence band and the bottom of the conduction band. And so these would be the orbitals that you want to apply the value of U to. So by resolving the band structure to the contributions of different orbitals, you can figure out which orbitals to pick for Bayesian optimization.
Okay, so basically you would have to do some initial HSE and PVA calculations anyway, and you just project to the region.
We have to do we have to do an HSE calculation as a reference for the Bayesian optimization, but we do that calculation only once for the bulk material, for the permeable cell, and then we go on and do the big interface calculation with the PV plus U.
And how, I mean, I imagine you must have tested this and done this quite a lot of times. So are there any materials where you get like some really unexpected U values compared to what usually is used in literature of like a couple of like 2 to 5 eV 4D materials or something?
So the negative U values for
I was pointing to that, yeah.
the p orbitals are somewhat perhaps somewhat unexpected. Although there have been reports of negative U values in the literature previously, but it's not widely used. The reason they're allowed is that the effective U is actually a difference between U and J. So if J is larger than U, it can be argued that a negative value is permissible. And then maybe you can rationalize it with the fact that how the self-interaction error works for d orbitals versus p orbitals, that d orbitals tend to be overly delocalized and maybe the p orbitals tend to be overly localized. It's not well studied, let's say on formal grounds, but empirically it has been found to work by us and others.
Okay, thank you. Makes a lot of sense, yeah.
Yeah. Okay.
So I think we can go on with the applications.
Okay, so in the remaining time, I have a few applications to show you for topological interfaces. So let's start with a crystalline topological insulator. The rock salt structure of tin selenide is an example of such a material. So topological crystalline insulators are materials that in the bulk are just insulators with a band gap, but on the surface, so here you can see a slab model of tin selenide with surfaces. And here you can see the band structures of this model. And you can see that on the surface, you get this conducting state with a Dirac point, and that's the topological surface state. And the reason you get it on the surface is that it breaks the symmetry of the bulk. So now we want to know if we can somehow open a band gap in this topological state in order to be able to use it for devices. So at an interface with a ferromagnet, the time reversal symmetry is broken, and then you can open a gap in this topological state. And you can see in this case, we open a little gap of 21 millieVs at the gamma point and 9 millieVs at the end point, with when it's interfaced with europium sulfide, which is a ferromagnetic insulator. And it may seem very small, but it's actually larger than the previously proposed materials combination. Another interesting thing about this interface is that when you, so this one was a periodic heterostructure model where you have interfaces on both ends. But when you have a model of the tin cyanide being grown on top of the europium sulfide, and then you have a top surface here, then you actually see that it's split into two Dirac cones. And the green one here is the one that's on the top surface. And you can see that it's not shifted and there's no gap in it. Whereas the one that's here in contact with the europium sulfide at the interface is shifted from the Fermi level and has a gap. So that tells you that this effect of the interface is very localized. You only get it at the interface, and then the top surface is not affected. So that's one story about topological insulators and how you can manipulate their properties by interfacing them with other materials. And then another story is what we call a 2D topological insulator. So that's a topological insulator phase that can emerge at an interface between two materials that are not topological insulators themselves. So here we have two materials. Cadmium telluride is just a wide gap semiconductor. And then mercury telluride is a semi-metal, and it has an inverted band structure, as you can see here, where the mercury S states form the top of this band here, and the P states form the bottom of this band, the tellurium P states. Okay, so what happens if you interface these two materials? Something very interesting. So if you have a small number of layers, you have just a trivial insulator at the interface. And here you can see the top of the valence band is made of the tellurium P states, and the bottom of the conduction band is made of the mercury S states. And as you start adding more and more layers, eventually you get this band crossing. And as you add more layers, you get this inverted gap opening with the band character changing. So here the bottom of the conduction band changes to tellurium P, and then the top of the valence band changes into mercury S. So at a critical thickness of 5.1 nanometers, you have this magic happening where two materials that are not inherently topological insulators silently produce a topological insulator phase, inverted band gap. And if you keep adding more and more layers of mercury telluride, eventually you'll get this bulk band structure. Okay. So the next question is whether a 2D topological insulator phase can be produced between two materials that don't even have an inverted band structure like the mercury telluride. So two completely regular, boring semiconductors, gallium antimonide and indium arsenide. So it has been proposed that under the right conditions, so at this interface, you can see that the top of the valence band is made of gallium antimonide states, and the bottom of the conduction band is made of indium arsenide states, because that's how the bands line up. So it has been proposed that under the right conditions, you could raise the gallium antimonide top of the valence band and lower the indium arsenide bottom of the conduction band and get these bands to cross and then get an inverted gap to open. And you would theoretically achieve this topological insulator phase. There's some debate over whether it's actually achieved in practice. And so we wanted to see by computer simulations, maybe what would be the right conditions. So we started by looking at trying to find a critical thickness where this band crossing and inversion might be achieved. And you see here, this interface, first of all, has two types of terminations, where the indium can be in contact with the antimony, or the gallium can be in contact with the arsenic. And it makes a difference which interface type you have. And so here you can see what happens if we add layers of either material. And when we add layers of indium arsenide, as you can see here, on top of 50 layers of gallium antimonide, the band gap does narrow, but it doesn't close. With up to 50 layers, which is 50 nanometers, we don't see a band crossing here. And it seems like maybe the asymptotic limit is going to be some finite gap here. The indium antimonide type interface has a narrow gap. So we can't get the bands to cross here just by adding layers of indium arsenide. The next thing we tried was adding an external electric field. So because of the computational cost of the simulations with the electric field, we can only do it for a model with 10 layers of each material. So that means that it has effectively a larger gap because of quantum confinement. So we're going to need a larger effective electric field to close the gap here. But you can see that if we apply a large enough electric field, we do get the bands to cross, and eventually we get an inverted gap to open. The inverted gap will widen but also shift higher above the Fermi level as you increase the electric field, which means that, first of all, you'll need a considerable electric field in order to produce this band crossing. And second, you would need to somehow tune into this gap, which is above the Fermi level, in order to observe it. So we tried to estimate what would be the effective field that might be needed for a larger interface model, just by looking at the change in the band gap versus the electric field. So here you can see the slab with the 10 layers of each material, the indium antimonide type interface, where you need a lower electric field here to close the gap than for the gallium arsenide type interface. And if you had the 50-50 interface with 50 layers of each material, then we estimate that you would need a smaller electric field to close the gap because it's narrower. It's a narrower gap to begin with. So this is how you would maybe be able to produce a topological state between two conventional semiconductors, but it seems like the conditions to achieve this are not trivial. So this brings me to the end of the story. So just to recap, I told you about how we predict the structure of epitaxial interfaces, and then what we do to predict their electronic properties with DFT plus U.
So, thank you, Noah,
Thank you.
for this great talk. So I actually raised my hand. I wanted to applaud. We don't have really much audience reaction, unfortunately, in the Zoom call because we have the audience on YouTube. But I think this, especially probably for computational tribologists, this Bayesian optimization of the U is tremendously interesting. I mean, not to mention the efficient sampling of interface structures. I mean, for now, in most of our simulations, DFT is still the gold standard, just standard PVE usually. But with basically no added cost to get more accurate band structures. It is quite exciting, I think. We actually do have a question in the chat now. That is, I think, referring. Yeah. Okay.
Just one more thing about the interface configurations. I think that for getting the right interface distance and registry, especially for the interface distance, the Van der Waals correction is probably more important than the DFT plus U. We do use the Van der Waals correction in our interface simulations, but then the U is critical for the electronic properties.
So I was actually going to ask about the Van der Waals corrections, and I was wondering whether the kind of do you use the standard post DFT Grimme correction, or you have other...
We use that Tkachenko-Scheffler correction.
Okay.
It's a pairwise correction similar to the Grimme correction, but the difference is in how the parameters of the correction are derived.
Okay, cool. Thank you.
We have I didn't show it today, but we have a paper on the indium arsenide europium sulfide interface, and then that goes into the details of that a little bit.
Is the Van der Waals, do you think the Van der Waals effects are also somehow affected by the number of layers that you manage to include in the extent of the Van der Waals correction?
We didn't really test that. We just kind of use a sufficient number of layers to converge it. We do find that it takes more layers to converge the electronic structure than to converge the structure. In order to reach the bulk limit where you don't have quantum confinement, it can take a very large number of layers, depending on the material. But we find, for semiconductors like indium arsenide and indium antimonide, something like 40-something layers. For materials where, for materials for semi-metals and topological insulators where you have to close a gap at the interface, it takes a very large number of layers. For alpha tin, for example, we find that it takes 80 layers to really close the gap. And then for for the topological insulators I showed you for this work, it also took a very large number of layers. I don't remember off the top of my head how many, but it's in the paper. We needed a very large number of layers to really close the gap at the Dirac cone.
Interesting. Thanks.
I think the question that is in the chat is somewhat related to this. I mean, this is going back to, I think, geometric optimization. So in the first part of your talk, when you talked about converging the, or actually, yeah, total energy, I would say it was probably the interface energy, so that you converge the interface energy with respect to both the top and bottom slab thickness. And the question is from Fiat Yalchin, and he asks, I was wondering if you have an intuition as to whether or not optimizing film and slab thicknesses separately, for example with respect to the surface energies, would give similar adhesion energies as your method.
So we find that optimizing them separately can lead to a different number of layers than if you optimize them together, which is why we do that. But the surface energy does also go into the interface energy, so we also have to optimize them for the surface energy separately.
So basically you have to do optimization for each of the slabs with respect to surface energy, and then with them together in all the combinations to get a total interface energy that you got that you're sure is correct.
Which again makes it a pretty expensive and time-consuming calculation. It's a lot of effort to calculate an interface energy, and that's why we have a kind of quick and dirty way of trying to estimate it without doing DFT calculations.
Yes.
And then you can do DFT calculations for your last maybe 1 or 2 or maybe 3 candidates if you really want to figure out which one is the right one.
Yeah, I mean, if you do a complex enough systems, even the calculation of a surface energy becomes complicated. Maybe, yeah, or at least cumbersome.
Right.
I'd say not complicated by the method, but
No
expensive.
doubt.
Yeah. Okay.
Yeah, we have another paper on surface energies of organic molecular crystals, where because the organic molecules are very large, when you start adding layers of a molecular crystal, it becomes really large really fast. So surface energy calculations also can become very expensive.
One small thing that when you talked about this in the last section about this this need for very large layer count. So in my experience, if I make my cell really large, I get really problematic convergence behavior, at least with VASP. I'm not sure what codes you use,
Right.
but this high asymmetry of the cell is not playing really well with the code, it seems. So do you see something like this, or is there a way to correct?
Absolutely. We do see convergence issues with some of these large interface calculations with VASP. We do use VASP. My students work very hard to try to figure out how to converge these calculations. And we did put in our papers the parameters, the flags we used in VASP in order to get them to converge. And it's especially tricky when you have magnetic materials. The calculations just can get very painful to converge, and like half the time the SEF doesn't converge. And we have a paper that we just put on arXiv last week on an interface between Heusler's and 3.5 semiconductors, and we in there we put the VASP flags that we used in order to get them to converge.
I will be sure to look that up just for that. I mean, also I'm interested in anyway in this work, but yeah, just because I mean I don't know if you know, but I'm also working part-time for the VASP company, so I'm also interested in
Oh,
like, special
I didn't know that.
complicated cases and test sets and so on. Okay.
Okay, well, if you also work for the VASP company, then I should mention that we have visualization package for VASP called VASP-Viz, and it's described in this paper in addition to a few other things. This paper is a review paper called Best Practices for First Principle Simulations of Inorganic Epitaxial Interfaces. And there's a lot of good advice for people who want to do simulations of interfaces. And also we use this VASP-Viz visualizer to make all kinds of nice plots with projections of the band structure on different atoms and different orbitals and different spin states. We can do interface layer by layer local density of state plots. They're also very nice for interfaces to see. They enable you to see things like band bending at the interface and metal-induced gap states and proximity-induced magnetism in the semiconductor, all these things. Also, it works with VASP and also can be useful for VASP users.
Okay, I think I've already seen the paper. I'm pretty sure I consulted it before for some specific questions I had. I'm not remembering now what these were, but I'm familiar with the title and I'm sure I've seen it. I would be interested. I will check out this VASP visualization tool. I mean, you might know that VASP is slowly switching to a different outputs format, HDF5, and with that comes also different analysis tools. But this is early stages, and of course, inspiration is always welcome. And third-party
I guess we'll have to update our package then. If the
I mean, no, not now, not so quick. There will be the old output files will continue to exist for some while, but I think we all can agree that the XML file is not ideally to parse. And yeah, so hopefully this will be easier in the end. Yeah, and there will be a nice Python interface and so on. Okay, with that, if there are no more questions, either from the panel or from the chat. In the chat, at least, I don't see anything. If you are in the panel, please raise your hand or just unmute yourself. But if there is no more, I think we're pretty perfectly in time to thank all of the speakers again with our very small virtual applause feature here. And especially thank Noah for the last talk. And with that, I say goodbye. Have a good day. And I hope to see you next Friday for the next and last session of WeSST 2022.
Right, thank you, Noah. Thanks to all of the speakers.
Thank you. Thanks again for inviting me.
Thank
Goodbye.
you. Bye.
See you next Friday.
Okay, have a good weekend, everyone.